So thank you, Felix, and thanks to all the other organizers. The organization's been great so far. I've been having a lot of fun. So I'm David. If you have questions, well, first of all, if you have questions, please shout at me, ask me. I encourage participation. If you want to ask something offline, send me an email. I'm also doing my best to type up my lectures, so tech up stuff. And it should be on this URL, but if you look at the Indico page, there should also be a direct link there, so you don't have to remember some complicated long expression. Okay, so I'll be talking about baryogenesis. And baryogenesis connects to the puzzle of why we're here, and specifically why there's more regular matter than antimatter. So fortunately, the stuff around us is regular matter. I don't have to worry about touching the table and some of you may have read the pinnacle of English literature, Angels and Demons, also about antimatter. Yeah, I actually have a colleague at TRIUMF who works on making anti-hydrogen atoms, and he's doing spectroscopy with them. Really neat stuff, but in any case, I'm off. Okay, so the neat thing, or the puzzle about the baryon density of the universe, I mean, you think about matter as being kind of the normal thing, and antimatter is this weird stuff. From the point of view of the Standard Model, though, antimatter and matter are treated in almost exactly the same way. So there's a little bit of CP violation that distinguishes between them, but essentially you treat them in exactly the same way. You could rename, in your quantum field theory, what you call particles versus antiparticles, and everything would basically look the same up to essentially one phase. And because of this, it turns out that, in this sense, antimatter is not weird enough, in that within the Standard Model, we don't know how to explain why there is more matter than antimatter. So this is a baryogenesis puzzle. And because we don't know how to explain it in the Standard Model, the fact that we're made of matter versus having a lot of antimatter around is very strong evidence for new physics beyond the Standard Model. So baryogenesis presents a cosmological puzzle. It also presents a very interesting particle physics puzzle. And it mixes particle physics with cosmology in a very interesting way, at least in my opinion. So before I get started, let me just say a few words on notation. I'm going to use standard natural units where h bar is c and the Boltzmann constant are all equal to 1. I'm going to use a mostly minus metric. So my apologies to you gravitationalists who like mostly pluses. And when I say Planck mass, I mean specifically the reduced Planck mass. So the 2.4 times 10 to the 18 GeV. And if you like, this is 1 over root 8 pi g. Okay. So having gotten that out of the way, let me move on to baryogenesis. So we know a lot about what our universe is made of from various cosmological and astrophysical probes. The thing that really pegs down what we know about baryons, and specifically the total baryon density of the universe, comes from measurements of the cosmic microwave background, the CMB. So for the CMB, you've all seen this power spectrum. There you have your L's, and then you have your something CL. And the CMB power spectrum has these bumps and wiggles, and these bumps and wiggles correspond to essentially the evolution of density fluctuations well, I guess before, during, and after recombination. And you can learn a lot from these bumps and wiggles. One of the things you can learn is the total baryon density. So within lambda CDM, the shapes of these bumps and wiggles depends on the baryon density of the universe. And for example, if you have more baryons, the relative heights, specifically of these peaks, would look different. So more baryons will look something like this, and I'm not going to be able to drill out. I've applied in my notes. But what we get out of this from the CMB, plus combining with other measurements within lambda CDM, is a very, very precise determination of the baryon density. So our baryon density, omega BH squared, turns out to be 0.0 2 to 3 plus or minus 0.00. Okay, it's a lot of zeros. 3 zeros or 2 zeros? Okay, anyway. I think I've got the right number of zeros. But in any case, we have a very good determination of the baryon density. And remember, this h parameter is essentially the value of Hubble today in slightly funny units. It's roughly 0.6967 or so. So h squared is about 1/2. And this corresponds to about 5%, oops, wrong way, of the current energy density of the universe is made of baryons. So this is also the 5% that consists of stuff that we think we know and understand. We still don't know or understand why you get the actual 5%. So this is where baryogenesis comes in. So because you'll see this a lot, I'm going to define a quantity called eta. And eta is the number density of baryons today relative to the number density of photons today. So you can get this by taking the baryon density. In this case, it's normalized to the critical density today. And then just renormalizing it to the number of photons today, which you can get from the CMB temperature. And this thing comes out to be about 6.1 times 10 to the minus 10. So relative to the number of photons today, we have very few baryons. But even though this looks like a small number, it turns out that there's a sense in which it's actually a very big number that I'll get to in a second. OK, so we have this determination of eta from the cosmic microwave background. We have a second independent determination of eta, the effective baryon density, from primordial nucleosynthesis. So okay, I'm probably jumping ahead of what you'll cover in the Lambda CDM lectures, but okay, you start with a hot early universe, and it cools off, it expands, yada, yada, yada. Once the temperature cools below about an MeV or so, free nucleons, free protons and neutrons, start to glomp together to make composite nuclei. And they build up and build up and build up, and you roughly produce light elements up to about lithium. And what you can do is take what we know about lambda CDM, take what we know about the evolution of the universe at temperatures below about 5 MeV or so, and combine this with what we know about nuclear physics, what we know about how protons and neutrons clump together to make light elements. And putting this together and doing very complicated nuclear physics and astrophysics calculations with the various complicated decay rate systems, you can make predictions for the light element abundances up to about lithium. And you take these predictions and you compare them to astrophysical observations where you think you're seeing primordial abundances of these light elements that haven't been reprocessed by stars. And when you make this comparison, the predictions that you get from primordial nucleosynthesis using lambda CDM with standard expansionary cosmology and what we know about nuclear physics, which we tend to know very well, is that this primordial nucleosynthesis, so-called BBN, Big Bang nucleosynthesis, works really well for this value of eta. So the value of, so the light element abundances that you deduce from primordial nucleosynthesis matches the baryon density that you get from the CMB. So I should say that when you compute the light element abundances in BBN, your free parameter is essentially the baryon density, corresponding to this eta parameter. So you let this float, and you make predictions as a function of eta. You compare to observations, and it turns out that you get a good match with observations for eta that also matches the value deduced from the CMB. So we have a nice, consistent picture of the baryon density of the universe. We have two independent determinations, so we're pretty sure we're right. This is also a very nice piece of evidence for lambda CDM and at least a standard cosmological history at temperatures below about 5 MeV. So these things tell us essentially about the total baryon density of the universe. But on top of the total baryon density of the universe, we're also pretty sure that this baryon density is basically all baryons with essentially no antibaryons. The antibaryons we see around you can understand from things like high-energy cosmic rays. Let's say a proton smacking into something and making some antiprotons as secondaries. So essentially, what I'm going to call NB is the number density of baryons minus the number density of antibaryons. And this thing, we're pretty sure is 0. So we're pretty sure it's 0 for a lot of different reasons. One, okay, we're pretty sure it's 0 around us because I'm not annihilating spontaneously. So our local region should at least be dominated by baryons. You can start to look further afield. As you look further afield, there are various ways to figure out that stuff farther out is made of baryons. If there were a lot of antibaryons around, they would annihilate with the baryons, and you'd see a lot of high-energy gamma rays or X-rays. And the fact that you don't see a lot of high-energy gamma rays or X-rays, with some other assumptions, basically lets us push out the radius around us that's made of baryons versus antibaryons to be very large. So okay, there's some interesting questions having to do with this, and people have tried to motivate the idea that maybe there are patches of baryons with antibaryons. This gets messy, and I'm going to go with the assumption that essentially a whole universe, at least in the observable patch, is made of baryons with basically no antibaryons. Now, there's one other piece of motivation to have baryons but not antibaryons, which is that if you started off with at least a mixture of baryons and antibaryons, you would not get this observed baryon density. And the reason for this is that baryons and antibaryons annihilate really, really efficiently. So for example, I get a pp bar goes to pi 0, or pi plus, pi minus, and you get secondaries. This annihilation process is really, really efficient. And if you do a freeze-out calculation, assuming you started with equal numbers of protons and antiprotons, you do a standard freeze-out calculation in complete analogy to the way you do standard freeze-out calculations of dark matter, which I suspect will be covered at some point later in the school. What you find is that this process happens, and it keeps on going and going, down to a so-called freeze-out temperature of about 20 MeV. And by the time you hit a temperature of about 20 MeV, the density of protons and antiprotons has gotten so small that there just aren't enough of them around to find each other to annihilate. And with this freeze-out temperature, and doing the freeze-out calculation, corresponds to an eta of something like 10 to the minus 19. So if we started with equal numbers of baryons and antibaryons and just let them annihilate with each other, what you would get is almost nothing. You get a baryon to photon ratio that's something like almost 10 to the 10 times, or let's say 10 to the 9 times too small compared to observations. So the picture we have instead is that we have an asymmetry. So at very high temperatures, we expect to have both baryons and antibaryons just produced through thermal collisions. And the idea for the asymmetry is that a temperature is greater than about, let's say, order 1 GeV, greater than about the baryon mass. You have roughly 10 to the 10 baryons plus 1 baryons for every 10 to the 10 antibaryons. And what happens is these baryons and antibaryons then come together. I'm going to get some red chalk for effect. The 10 to the 10 and 10 to the 10, the symmetric part, just annihilates completely, and you're left with this one remainder asymmetric bit. So what happens in the asymmetric scenario is that the symmetric part of the densities annihilate away as you cool below the baryon mass. And only the asymmetry remains at the end of the day. So this asymmetric picture can explain the right baryon density, provided you have a big enough asymmetry. So the size of the asymmetry, as I said, isn't terribly large. At temperatures above a GeV, you need roughly 1 extra baryon per 10 to the 10 total baryons versus antibaryons. And the puzzle of baryogenesis is how does this come about? So ultimately, the goal of theories of mechanisms of baryogenesis is to explain this extra baryon for every 10 to the 10 antibaryons, presumably at temperatures above about a GeV. Question? Yeah. Okay, so it's not exactly 10 to the 10, but it's related to this 10 to the minus 10. So 1 part in 10 to the 10. Yeah. So so I've dumped a bunch of order 1 numbers, but roughly at temperatures above the mass of a particle, everything has a density of about temperature cubed, a number density about temperature cubed. So the number density of baryons up to degrees of freedom would have been the same as the number density of photons. So again, I'm being sloppy with order 1 numbers, but the 10 to the n here is essentially 1 over that. Okay. Number densities. I'll get to this in a little bit. Roughly on dimensional grounds, though, a number density in my natural units, a number density in natural units has units of energy cubed, and a temperature is much larger than a mass of anything around. The only dimensional scale is the temperature. So essentially, very high temperatures compared to the mass of a particle, the number density ends up going like t cubed. And that's my dimensional argument, but I'll come back to this in a few minutes, and Matthias will cover this in more detail when he talks about lambda CDM. Okay. Okay, so the question of baryogenesis is, how do we get this extra 1 part in 10 to the 10? And this is what I'm going to cover for the rest of these lectures. And I'm going to give a somewhat biased view. So just to get to my outline, today I'm going to try to give you an overview of baryogenesis. And specifically, I want to talk about the ingredients you need for baryogenesis, and talk about specifically how these ingredients come about within the standard model and where the standard model doesn't quite fit the bill. So I'll do this today and possibly a little bit into the next lecture tomorrow. The other topics I plan to cover are 2 specific mechanisms of baryogenesis. These are probably 2 of the most popular ones. The first is a mechanism of baryogenesis, a way to get the baryon excess called leptogenesis. And at least in the minimal scenario for this, you have very heavy right-handed neutrinos that decay in the early universe, that produce a lepton asymmetry, that then gets converted into a baryon asymmetry. And the nice thing about leptogenesis is, at least within the minimal realization, there's a very nice connection between the mechanism to create the baryon asymmetry and the origin of neutrino masses. So I'll probably spend a lecture, maybe a little bit less than a lecture on leptogenesis. And then the third mechanism I want to talk about, or the second mechanism I want to talk about in detail, is electroweak baryogenesis. So what happens in electroweak baryogenesis is you start off with a very, very hot universe, presumably with temperatures well above the weak scale. And it turns out that at temperatures well above the weak scale, the minimum energy configuration of the Higgs, or I'll say the minimum free energy configuration of the Higgs, corresponds to no net Higgs expectation value. And put another way, this means that the electroweak symmetry of the standard model is restored at very high temperatures. Now, as you cool off, you cool below about the weak scale, and you go through a phase transition, where you go from unbroken electroweak symmetry to broken electroweak symmetry. And when this occurs, if it occurs in a somewhat violent way through a first-order phase transition, it turns out that the dynamics having to do with that phase transition can give you a means to produce the baryon excess. So I'm going to spend probably a couple lectures on electroweak baryogenesis, time permitting. Electroweak baryogenesis is the mechanism I've probably worked on the most, so I'm a biased observer, so let me warn you about that. The other thing, though, that's nice about electroweak baryogenesis is that the elements that go into it are very measurable at experiments. So things like the LHC or searches for new sources of CP violation. And I'm going to try to make the nice connection between what you need for electroweak baryogenesis and what you would look for in current and upcoming experiments. Okay, so this is my brief outline. So let me get back to overviewing baryogenesis. So it's actually realized quite some time ago that unless you plan to do something really, really weird that I don't want to get into, you basically have to fulfill 3 conditions to produce the baryon asymmetry, the baryon density. And these 3 conditions were formulated by Surhoff, and they're known as the Surhoff Conditions. And he came out with them back in 1967. So the first condition, I think, should be fairly intuitive, which is you need to violate the baryon number, the apparent baryon number symmetry of the standard model. And the motivation for this is we think that inflation happened. And inflation, I guess Matthias will cover this. In inflation, you essentially, inflate, but as you inflate, you dilute basically everything you started with, and you start afresh. So you inflate, you reheat, you return to a thermal state, and if you want it to be sneaky and postulate some sort of weird quantum gravity initial condition baryon excess, this kind of thing is going to be just diluted away through inflation. So we have the picture in mind that we start with essentially a post-inflation universe that essentially has no baryon excess because inflation would have diluted it away. And we want to go from this universe with zero baryon number to one in which we have a non-zero baryon number. So to go from 0 baryon number to non-zero baryon number, you need to violate baryon number conservation. The second condition is C and CP violation. And the idea here is to give you a bias. So it turns out that if you just have processes of the violate baryon number, in general, there's no reason for the process of violates baryon number to make more baryons than antibaryons. C and CP violation come in as the way to bias these baryon number violating processes to make more baryons than antibaryons. And third, you need a departure from thermodynamic equilibrium. So again, this one's a little bit subtle. One way to think about this is if you have thermodynamic equilibrium, nothing changes. So if we start with 0 baryon number after inflation and nothing changes, well, you're not going to get any baryon number. That's a little bit too simple. In practice, we're going to see that you need departures from thermodynamic equilibrium to make sure that when you make baryons, they don't get washed out by reverse reactions. So these elements are going to come up when I discuss specific baryogenesis mechanisms. These are the general ones, but we'll see them realized in different ways in different mechanisms. So if this stuff is still a little bit fuzzy, just hold tight, and hopefully the way these aspects play a role in certain mechanisms will become more clear when I actually illustrate them with specific mechanisms. Okay, so I want to talk a little bit more about these 3 elements. It turns out that all 3 of them are present in the standard model. It turns out the standard model actually does have baryon number violation. We know the standard model has C and CP violation. The C violation comes from the fact that we have essentially chiral representations of SU2. We also have CP violation from the phase in the CKM matrix. And at the very least, we have departure from thermodynamic equilibrium simply from the fact that our universe is expanding and there's an arrow of time and that we're going from a hot universe to a cold universe. So the standard model actually has all of these elements. But having said that, we don't know of a mechanism that operates within the standard model alone that can produce the baryon asymmetry even though these elements are present. So because I want to go beyond the standard model, but I also want to give you a feel for how this stuff comes about in the standard model, I'm going to start off by going over these elements within the standard model and try to give you an idea of why the standard model still doesn't quite work. Okay, so let me start off with baryon number violation. So if you think I'm talking nonsense because I tell you that there's baryon number violation in the standard model, I don't blame you, but there is. There's baryon number violation in the standard model, but it comes around in quite a subtle way. So I want to spend a little bit of time on how this baryon number violation does occur within the standard model, because for all the mechanisms of baryogenesis I'm going to talk about, this baryon number violation within the standard model is going to play an important role. So baryon number specifically is a U1 symmetry, usually called U1b, under which your quark fields just change by a phase. So it's just a regular old garden variety U1. This applies to left and right-handed quarks. The leptons are neutral under this. There's also corresponding U1 lepton number, under which your leptons have lepton number +1, and the quarks don't transform. So you've got your lepton number, you've got your baryon number. And then you can think about linear combinations. You can think about B plus L, B minus L, and so on and so forth. So now, a neat feature of the standard model is you go off and you write down your standard model Lagrangian, and you keep it at the renormalizable level. So you keep only operators up to dimension 4. It turns out that the matter content of the standard model plus gauge invariance under SU3 cross SU2 cross U1 implies automatically that U1b and U1l are symmetries of the classical Lagrangian. So it turns out that as soon as you write down all the renormalizable operators you can within the standard model that are gauge invariant up to the renormalizable level, these are automatic so-called accidental symmetries of the theory, in that you didn't have to do any work to put them in. They just happen to be there. You're stuck with them. So when I say these are good symmetries, I mean specifically both of these are good quote-unquote classical symmetries. And what I mean by classical symmetry is that if I take my action for the standard model, and it depends on your fermion fields and your Higgs field and your vector boson field, and I apply a U1b or U1l transformation to it, I get back the same thing. Oops. So as far as looking at the standard model as a classical field theory, this is a perfectly good symmetry. But it turns out that these transformations are not good quantum symmetries of the theory. So in my quantum field theory, there are different ways to think about this, but in my quantum field theory, instead of just having an action, I have a path integral too. So to define the quantum theory, I have some path integral with some fermions and other stuff, and then I weight all this stuff. I weight all this stuff by the exponential of the action. So I got my path integral formulation of the theory, and now suppose I do a U1b or U1l transformation on the theory. What ends up happening is when I do this transformation, this object doesn't change. I'm good to go. But it turns out that this object does change. So even though my action is invariant, and the e to the I as standard model part of the action is invariant under these transformations. My path integral measure is not invariant. So in a sense, I don't want to get into. The non-invariance of the path integral measure is closely related to defining how you regularize and renormalize the theory. But in any case, it turns out that this path integral measure is not invariant. And that means that my full quantum theory is not actually invariant under B and L transformations, even though naively I might think it would be, because my action is perfectly good. So I should say that usually it's the case. Okay, I don't know what the measure of usually is, but it's usually the case that if you have a good classical symmetry, it's also good quantum symmetry. But there are certain specific classical symmetries that are not good quantum symmetries. These are usually connected to chiral fermions, at least in the particle physics context. And when this happens, we usually say that the corresponding would-be symmetry is anomalous. Anomalous. So anomalies are really interesting things on a lot of different levels. They really neat physical meanings. Now, I should also say that calling something an anomalous symmetry is it's a bit of a bad terminology, because if a symmetry is anomalous, it's not actually a symmetry because you don't actually have the physical invariance. But people still say anomalous symmetries. So the way you actually see this in practice, though, is you look at the would-be Noether currents corresponding to baryon and lepton number, and you look at their divergences, and you compute the divergence of these would-be Noether currents, which should be 0, sandwiched between certain matrix elements. And you find that certain matrix elements of the divergences of the currents don't actually vanish as they ought to for a genuine symmetry. So let me write down my currents. So based on the invariance of the classical Lagrangian, I'd be inclined to write down standard Noether currents, and these have the following form. For Baryon number, put a bracket around this, where this I is the sum over the generations, over the family. So I've got contributions to the current from the left-handed quark doublets and the right-handed up quarks and right-handed down quarks. Just usual thing, and I've got a contribution for each generation. And similarly for lepton number, I have a similar sum over generations, and I've got contributions for the left-handed leptons plus the right-handed leptons. So these are just the Noether currents you would write down for the classical field theory corresponding to the conservation of B and L at the classical level. Now, what ends up happening at the quantum level when you compute matrix elements of the divergences of these currents is you find a non-zero result. So the standard Noether theorem result is that the divergences of these currents should be 0. But it turns out that quantum mechanically, they're not. And the result at the end of the day turns out to be this. 32 pi squared. Where this is the U1 field strength. This is the SU2 left field strength. This is the SU2 left gauge coupling. This is the U1 gauge coupling. This NG is 3, is the number of generations. And, oh, I forgot tilde. So the tilde here means the dual field strength. And in general, an A tilde mu nu is, actually, I guess I want to write this upstairs, is a 1/2 epsilon mu nu alpha beta A alpha beta. So, okay, is this too small? No, okay. So the tilde of a field strength is you take the field strength, which if you recall is antisymmetric, and you contract it with the 4-index antisymmetric tensor. And just to warn you, my convention is epsilon 0, 1, 2, 3 is +1. Some people use -1, so sometimes you'll see the same expression with minus signs. Okay, but in any case, this is the quantum mechanical result. And instead of getting 0, I get these funny WW tilde, BB tilde. And the fact that I get a non-zero result is simply a statement that my would-be B and L objects, or my would-be B and L transformations, are not actually symmetries of the quantum theory. So this is nice, but at the same time, it's a bit puzzling, because it seems like whenever you look at the standard model, you don't see baryons just disappearing. So it seems like baryon number is a really, really good symmetry, and I just told you that it's not.
Can you remind me how this result comes about?
Yeah, so computing these is, am I allowed to, okay, I probably shouldn't draw here. So, okay, there are different ways to derive this result. One way is to actually go to the path integral and actually deal with the change in the path integral measure. So this is kind of sneaky. A more direct route is to compute loops. And the loop you would compute is this thing. This current looks like a vertex where you have two fermion legs coming out like so. So I take this vertex and I connect it up with matrix elements of various external states, and I don't necessarily know which ones to choose, but okay, let's say you take this and you compute all kinds of matrix elements until you're run out of matrix elements. Eventually you find that one loop, you take the vertex corresponding to the current that has a mu index, and you connect it up to a pair of vector bosons with the adjoint index A and B and Lorentz index mu and nu. And it turns out that this thing, actually I shouldn't call it, okay, I'll call this alpha. It turns out that this object is non-zero with if you like a momentum structure, if you compute this in momentum space, that corresponds to these operators. So the thing that corresponds to this result, this is the operator result. In practice, the way it was discovered was people went off and computed a bunch of diagrams, and they realized that this matrix element corresponding to what is essentially, for example, W mu A, W mu B, del alpha, J alpha B, 0 is not equal to 0. And the result they got for this matrix element, which corresponds to this diagram with two external vector boson legs, and then this insertion here, has a momentum structure corresponding to this as an operator. So, there's no tilde here. The tilde comes in that if you look at the momentum structure of this, it corresponds to the momentum structure you would get from using this operator. Yeah. So yeah. So it turns out that so I should say that this anomaly, this result, is related to the fact that you have chiral fermions. So you have different charges for left versus right-handed states. In the case where you do have we have non-chiral fermions, you end up getting 0 here. And in the case of QCD, the things contributing to the baryon density under QCD have are non-chiral. So there's no QCD contribution to it. So okay, there will be some interesting QCD dynamics similar to what I'm going to get to in a second, but it doesn't change baryon and lepton number. Okay, so going back to this, this is our result for non-zero. This is our result for the non-conservation of baryon and lepton number, and it might be a little bit disconcerting because again we're not decaying away. People have gone off and tried to measure decays of the proton. They haven't found anything, and the current limits on proton lifetimes are something like 10 to the 34 years. So if you recall, the age of the universe, if I have it right, it's about 10 to the 17 years. So we know the protons last much, much longer than the universe has been around, by orders and orders of magnitude. So the question then is, if I have this result, and the standard model seems to be breaking baryon and lepton number, why am I not seeing proton decay happening or other bad things like that? And the answer is that the way this, the way baryon and lepton number are violated, the mechanism by which you actually have this happen, occurs in a very, very subtle way that I want to spend a little bit of time on. So I'm going to have to make a bit of a digression, a bit of an aside, to talk about the structure of non-abelian gauge theories. But before I do that, let me just make one. Let me just tell you one kind of interesting thing about these field strength dual results, and that is that if I concentrate on, let's say, the SU2 part, it's going to be the SU2 part that we're going to care about. This SU2 part, g squared over 32 pi squared, w mu a, w tilde a mu nu. It turns out that you can write this as the divergence, the total divergence of a 4-vector. So this takes a little bit of fiddling to show, but it turns out that there exists a 4-vector such that when I take this total divergence, I get this back. So you might be thinking, okay, great, I can just write this as a 4-vector and then redefine what I call my currents, and this redefined current is going to be conserved. But not so fast. And the reason I say not so fast is, let me now write down my expression for my, what I call K2 mu, this thing that arises in this equality. This thing turns out to be g squared over 32 pi squared. And that's just this piece, times a friendly epsilon. W, let's try to get my indices right. U alpha, W beta A minus G over 3. Okay. Sorry, I'm trying to get, there's still a lot of indices to deal with. Okay, I'll just write it down here. Sorry, I'm getting excited and writing big. And alpha beta. Okay, so this is the result for the K2 mu. And if you sit down and you carefully differentiate it and fiddle with asymmetric stuff and so on and so forth, it turns out you get back this WW twiddle. So the thing about this K2 that doesn't let you redefine your currents in a sensible way is that if I look at this thing, here I have a nice field strength. So if you recall, field strengths transform in sort of a well-behaved way under gauge transformations. So I can make nice gauge invariant things out of field strengths without much problem. The fields themselves, so remember, this is not a field strength. I only have one index here. This is the actual vector field. This thing transforms in this really messy, non-homogeneous way under gauge transformations. And if you think back to, for example, electromagnetism, the field strengths correspond to E and B fields that are, if you like, physically observable, but the vector fields are not physically observable. They're gauge dependent. I can change around their values by making gauge transformations, and you typically don't want to touch some of the 10-foot pole when you're talking about physical observables. So this thing, K2 mu, is a big ugly, oh, sorry, I should, actually, right. This thing is a big ugly gauge dependent thing. And because it's gauge dependent, it doesn't have to have a nice behavior as I go off to infinity. So remember, the thing that lets us convert currents into conserved charges is the fact that usually, for well-defined field configurations, as I take them off to infinity, they go to 0, and that means that I can integrate by parts and dump my boundary terms. So I can usually do this, but I'm not necessarily allowed to do this for for gauge fields. And the reason I'm not necessarily allowed to do this for gauge fields is that physically my field strengths have to go to 0 at infinity to give me a well-defined finite Euclidean action configuration, but my my gauge fields themselves don't have to have any particular limit as I go to infinity. They don't necessarily have to go to 0. And this means that this thing can do all kinds of weird, messy things as I go off to infinity, and I'm not allowed to just integrate by parts because I'll probably get the wrong answer. So in any case, this is a kind of a messy gauge-dependent thing. But I'm going to nevertheless use it to define something in a second connected to the structure of non-abelian gauge theory vacua. But let me just back up. So again, we have non-conservation of B and L. And this implies the independent breaking of B and L of the standard model. Let me just mention in passing, though, that I could define a linear combination of B and L called B minus L that is a good symmetry. Because if I do an equal B and L transformation with an opposite sign, these changes cancel off, and this actually is a good quantum symmetry. Whereas the orthogonal combination B plus L is no good. So I'll come back to this in a second. So going back to this K2 mu, I'm going to have to deal with this, I'm going to have to talk about the vacuum structure of non-abelian gauge theories. And okay, again, let me apologize about this in that this is a big, complicated topic that people spent years and years understanding, and I'm trying to cover it in half an hour. But at least I want to give you an overview of the idea behind it. So there's a really neat story about the vacuum structure of non-abelian gauge theories that connects directly with the fact that this K2 mu can have a weird limit as you go off to space-time infinity. So I'm going to define something called NCS as the spatial integral of the zero component of K2. And this thing is a messy gauge-dependent thing. But it turns out that it has a very interesting limit if I focus on vacuum configurations. So vacuum configurations correspond to configurations where my field strength vanishes. So I can get rid of this term. And suppose I also choose a gauge in which I focus on vacuum configurations, and I choose a gauge where the zero component of my vector field vanishes. So it turns out I can do this as a I can make a gauge choice for this to happen. And these two conditions imply that my remaining A fields have the structure of 1 over IG U grad U inverse, which corresponds to a gauge transformation of a zero gauge field. So if I take this and I plug it in here, I get something that looks like minus g cubed over 96 pi squared integral d3x epsilon ijk W. Sorry, I'm getting all messed up with my indices. Oh, okay. Actually, I've got to type in my notes, which is why it's messing me up. Wi, Wj, Wk. Okay, so I get this complicated, messy object, but the thing to notice is that the way I'm contracting up the Lorentz indices, the spatial indices in this case, is actually the same way as I'm connecting up the gauge indices. So it turns out that this object actually has a very interesting mathematical, mathematical interpretation when I plug in gauge fields of this form. So, okay, I probably shouldn't go into too much detail, but the upshot of this is that when you look at the structure of this object, for these nice configurations, what you find is that the vacuum structure of non-abelian gauge theories is non-trivial, and that we have an obvious vacuum configuration of a gauge field, of a non-abelian gauge theory where I just set my vector field to 0 everywhere. This is okay, obviously there. This obviously gives me a 0 field strength. But it turns out that there are other non-trivial configurations of the vector fields that give me 0 field strengths that correspond to vacuum configurations. And what you get at the end of the day, and this is very non-trivial, and again, it took people many years to figure out, is that the vacuum structure given by an energy functional of the vector field configuration looks something like this. It has this funny periodic structure. Where I can label these different vacuum states by integers. And we conventionally take this 0, 1 corresponding to just a 0 vector field. And we call this integer that labels the vacuum state NCS. The CS stands for Chern-Simons. So this turns out to be the vacuum structure of a non-abelian gauge theory, either SU2 or anything with an SU2 subgroup, which turns out to be just about any non-abelian gauge theory. So first of all, we see that there are different vacuum states for this non-abelian gauge theory. The second really neat thing about non-abelian gauge theories, beyond just having these different independent vacua, is that it turns out that there also exist non-vacuum configurations of the gauge field that take you from one vacuum to the other. So to go from one vacuum to the other is not a vacuum configuration, but what it does correspond to is a tunneling configuration. So it turns out that there are configurations of the gauge field with finite Euclidean action. The Euclidean action is the thing that goes into tunneling. They take you from one vacuum state to the next. Where's my eraser? And these special configurations are called instantons. They're called instantons because they, if you like, they turn on and off. They're kind of like a little ball of, I don't know, non-zero field strength that sort of goes from 0, turns on, turns off, so they only last for an instant. So the upshot of this is we have non-trivial vacuum configurations of my non-abelian gauge theory, and we have configurations with finite Euclidean action that take me from one classical vacuum state to the next that correspond to tunneling, called instantons. So
this NCS can take values along the continuum. It's not restricted to these instanton solutions take it from continuously from one to another.
So okay, so I've defined this NCS very generally, but if I restrict it specifically to vacuum configurations, it's forced to take an integer value. So okay, if I'm not on a vacuum, if I don't have a vacuum configuration, who knows what this thing's going to be? It's a messy gauge dependent thing. But as long as I stick to a vacuum configuration, it has to take an integer. And it turns out that there's a neat topology reason for this, having to do with mapping essentially the structure of space-time infinity to the structure of the SE2 group space. It turns out that it ends up being a map of the 3-sphere to the 3-sphere, and there's all kinds of interesting mathematical topology of this, but there's a topological reason why you have to get integers. So again, this is a big topic, and okay, I can't do it justice, otherwise I'd spend 4 lectures on it. But okay, this is the story. Yes?
Why is K2 mu gauge dependent? Double tilde looks like gauge independent.
Well, so this is the field strength, so it's gauge covariant, but I have field strengths. Yeah, so this is gauge invariant. So it turns out that so the K2 on its own is gauge dependent. It turns into something that is gauge invariant when I take its derivative. So roughly what happens is when I take the derivative, the gauge dependent of this piece cancels against the gauge dependence of that piece. But only when I take the derivative. If I don't take the derivative, I'm stuck with gauge dependence.
Why are we just worried about the B dual terms there? We want to come up with a for the first term.
Yeah, so that's a good question. Yeah, I was going to get to that, but roughly the story there is if I go back to this expression, and this is a gauge-dependent thing, but we're going to worry primarily about the structure of this thing as I go off to space-time infinity, because that's the thing I worry about when I deal with another currents, when I integrate by parts. Now, this epsilon CAB is the SU2 structure constant. And for U1, there's no structure constant. So the corresponding expression for what you call a K1 mu wouldn't have this term. It would just have a B nu alpha, B mu, sorry, B beta, yeah, B nu alpha. It wouldn't have this piece. And that means that because it has a field strength, it's forced to go to 0 at infinity. So actually, in fact, this part, we don't actually care much about it because it actually is well behaved at infinity. Whereas the SU2 piece, specifically because of this piece, which is what goes into this thing defining the NCS, is not well behaved at infinity. It doesn't necessarily have to go to 0, and not going to 0 is connected with having different NCS values. Okay, so my apologies, I'm going to erase this. Okay, hopefully not about that. Okay.
Between these vacuum states has finite channel energy.
Yeah, so this is true, but it's non-trivial. So I'm asking you to take this on faith, but essentially it has finite energy in the sense that you can go off and find non-vacuum configurations that connect between the two, that have finite energy.
So it's like, if concerned the topology, like how can you come from the one topological charge to another? So it has non-trivial configuration on infinite, right? So it breaks in this way.
Yeah, well, so the topological argument applies specifically to vacuum configurations. If you relax from that, if you allow non-vacuum configurations, you can go from one topological vacuum to the other. So but the topology applies specifically to vacuum configurations. So for vacuum configurations, topology gives me these independent numbers. But if I deviate from the vacuum configuration, I can connect from one to the other. OK, so what we're going to do now is go back to our Noether equation with this thing, with our fancy NCS stuff, and look at what happens to the baryon charge. Oh, sorry, question? OK, so yeah, this is maybe not a useful equation. So it turns out that if you plug this expression into here, and you spend a lot of time in mathematics grad school, it would look like something familiar. But OK, well, I'm writing it because I have to. OK, this is probably not so illuminating, but it turns out that when I plug this in here, this ends up looking like essentially a Jacobian connecting essentially a 3-sphere to the group space. OK, but OK, remember this thing. Don't worry about the formula. Okay, so this is the important physics that you don't need years in grad school to understand. Mathematics grad school to understand.
How are we defining vacuum here? Sorry,
So in this case, lowest energy classical configuration.
That's a local minimum.
Yeah, well, so actually, yeah, so specifically, these are classical vacua, in the sense that I'm looking at classical field configurations. And these are all degenerate, so they all have zero energy with appropriate normalization, just separated by the periodic thing. So yeah, so my definition of a vacuum is just lowest energy state. And if you recall back to E and M, your Hamiltonian is something like E squared plus B squared. This generalizes to non-abelian gauge theories, and essentially your vacuum configuration corresponds to zero generalized E and B, which correspond to essentially zero field strengths. Okay, in any case, we have got our instantons that bring us from one to the other. So this is our classical configuration. Let's go back and use what we know about this here and plug it in here. So remember, the charge corresponding to another current is just the 3 integral of the zero component of the corresponding another current. And let's look at the change in baryon number of charge going from time minus infinity to time plus infinity. So specifically, let's look at delta B as the integral from minus infinity to plus infinity dt of my baryon charge, which is going to be a d3x j0b, and then I put in a time derivative. So here's a time derivative, and remember, when a time derivative hitting the integral is going to just give me the value of b at t equals plus infinity minus b at minus infinity. So by this, I mean b at infinity minus b at time equals minus infinity. So here's my charge. I put in a derivative here and then integrate, and this just gives me the value of this thing at the time endpoints. OK, so now I take this, and I use the fact that my d mu j mu of this is going to be given by the spatial gradient of the spatial components of this plus that. So this thing turns out to be minus infinity to infinity dt integral d3x of grad jot jb plus my ng over 32 pi squared, blah, blah, blah. And this has a time derivative hitting it, too. Actually, sorry. No, that's fine. D0, B, D0, D0. OK. I think I'm missing a piece here, but don't worry about this. So this thing I can turn into, by the divergence theorem, this thing I can turn into a boundary term that goes away. And this other piece, actually, no, sorry, this is correct. So this other piece is just the left side here. This other piece, I can write it as a del mu k mu. So unfortunately, I erase this. And this thing becomes a using that previous definition that I unfortunately erased already. And now I can go to town with this using my divergence theorem. So I'm going to turn this thing into a d4x, because integral dt d3x is just a d4x. And it turns out, OK, I'm going to come back to this, but this piece is going to vanish. And I can rewrite this as a d0 k02 plus grad dot k2. So this is all well and good. Now, to make my life easier, I'm going to choose a gauge. And I'm allowed to choose a gauge because this thing comes from this, is actually precisely this, and this thing is gauge independent. So here I have a nice contraction of field strengths with the adjoint indices contracted, and that means that this thing is gauge independent, so I can choose to evaluate this in whatever gauge I like. So I'm going to go back to my nice I'm going to go back to my nice so-called temporal gauge, where the zero component of where the zero component of the gauge field the zero component of the field strength vanishes, and it turns out that when I choose that gauge, this piece cancels off. Okay, you have to do some fiddling to show this, but okay, you can go home and exercise, go home and do it. So I'm left with this piece, but if I look at this piece,
Is there a sign in that? Is that a minus?
oh, sorry, yeah. Yeah, it's 0 anyhow. Okay, it's minus 0, yeah. Okay, I should also say that if you look at my notes and see typos, they're probably typos. I'm sure they're typos. Yeah, send me an email. Exercise. Okay, so back to this. D3x K02 brings me back to this. And it turns out that this thing I can rewrite as, okay. So, okay, I unfortunately erased my K2. So my K2 was this. So the K1 is the corresponding thing for this. Sorry. Okay. But okay, so it happens to be ignorable, so I'm going to ignore it. So it's ignorable because I can write it as a boundary term, and because I only have field strengths, it has to go to 0. Okay, so I'm stuck with this, but I recognize this as I have my d4x, which I can write as minus infinity to plus infinity dt d3x. And remember, I have my definition of K02 given by this. And this ends up giving me NCS t goes to infinity minus NCS t goes to minus infinity. Because again, I take my time derivative and I use it to unfold the t t integral. So, oh, actually, and I forgot my ng, my number of generations. Okay, so one last thing is normally this NCS thing is some messy, complicated thing that does all kinds of weird stuff. But because my time is going to plus or minus infinity, this is a boundary. And that means that I have to go to a vacuum configuration. For any reasonable field configuration, I have to go to the vacuum here. So I can do two things. So first of all, I've chosen the so-called temporal gauge. But the other thing is because I'm going to, if you like, a part of the space-time boundary, I also have to asymptote to field configurations that correspond to vacuum configurations, which means that this thing brings me back precisely to one of these vacuum configurations, NCS here. So the story at the end of the day, and okay, I'm running out of space here. I don't know what I want to erase. I want to erase. Okay, I don't want to erase this, okay, but I have to erase stuff. The result at the end of the day is that my delta B, going from minus infinity to plus infinity, is ng times delta NCS, where this delta NCS is a well-defined thing going from vacuum configuration at minus infinity to vacuum configuration at plus infinity. And I know that based on this structure, it's going to be some difference of integers. So this thing is some integer number, and this is just the number of generations 3. And I know that configurations that go from one vacuum to another correspond to tunneling. So what I get at the end of the day, this has been sort of a long-winded technical story, but what I get at the end of the day is that the violation of baryon number within the standard model corresponds to these instanton tunneling configurations going from one SU2 gauge theory vacuum to another one. So the story is whenever this tunneling happens from one classical vacuum to another, I change the baryon number, in this case by 3 units times the number of Chern-Simon number, times the number of vacua I jump in that tunneling configuration. So this is how baryon number violation happens in the standard model. It's a long, somewhat convoluted story, and it's related to this very subtle, non-trivial vacuum structure of non-abelian gauge theories. Okay, let me emphasize that there are whole books on this. Mathematicians have spent a lot of time on it, and I'm doing this in half an hour, so okay, if it's kind of fuzzy, don't worry about it. The moral of the story, though, that I want you to take home is that this is the SU2 vacuum structure, at least classically, and instantons jump from one to the other, and each time an instanton happens, I change the baryon number by 3 units times whatever integer jump I have, which also happens to be the same as the number of the change in my lepton number, again, through this equation. So this is how baryon number violation happens in the standard model. The next question, though, is how fast does it actually happen? And fortunately, it doesn't happen very quickly at all. So I can finally erase the stuff here. It doesn't happen very quickly at all. And if you think back to computing tunneling, okay, you may have seen tunneling in quantum field theory. You may have only seen it in regular standard one-particle quantum mechanics. But roughly, a tunneling rate is proportional to the Euclidean, the exponential of e to the minus Euclidean action of the field configuration that brings you from one vacuum state to the other. And I told you that there exist field configurations called instantons with finite Euclidean action that take you from one vacuum to the other. And it turns out that the instanton for a jump of 1 the Euclidean action goes like 8 pi squared over g squared, where g is the SU2 coupling constant. Okay, sorry, actually I lied. So the rate's actually this squared. The amplitude goes like e to the minus s Euclidean. The rate goes like this squared. So I take this and I plug in e to the minus 8, or I should say 16 pi squared over g squared, and I find a number that's really small, something like 10 to the minus 160. So the standard model has baryon and lepton number violation in it, but there's a dimensionless prefactor that goes into the rate that's something like 10 to the minus 160. So this is why we don't see baryon and lepton number violation in the standard model. It's just crushed by such a small number, its rate is unobservably small. So this is nice. We're not just decaying away spontaneously. Okay, these lectures are becoming very existential. We're not annihilating with antimatter. We're not decaying away. In this case, thanks to this very small factor. But this is only the story at 0 temperature. So today we're effectively 0 temperature compared to the scales involved here. At finite temperature, like happens in the early universe, instead of having to tunnel through, I can go over, like so. So instead of tunneling through from one vacuum state to another, I can have a thermal fluctuation that takes me over the barrier. And these thermal fluctuations that take you over the barrier, when you compute their rate, you end up essentially using something that looks like the action of the field configuration at the top of the peak here. And these configurations are called sphalerons. And sometimes, or very often, these finite temperature jumps at non-zero temperature are called sphaleron transitions. Or I'm just going to call them sphalerons for the most part because this is what people do in the field. So what ends up happening in the early universe at very high temperatures is instead of being crushed by this huge tunneling factor, instead I compute the thermal transition rate, effectively a classical thermal transition rate. And the rate can actually be pretty big in the early universe at high enough temperature. So people spend a lot of time computing these rates. For the sphaleron rate, the energy of the sphaleron configuration corresponding to kind of the top of this peak and let me just look this up. So the sphaleron configuration for the SU2 theory depends both on the Higgs field configuration and the vector field configuration. And if I have a Higgs vacuum expectation value, V, that generally depends on the temperature, the energy of the sphaleron configuration looks something like this, times some function of some order 1 function that depends on the ratio of the Higgs mass to the W mass. So this thing is just some, let's say it's roughly 1. Okay, so this is my Spalaron energy. And my Spalaron rate, or I should say my rate per unit volume, goes something like T to the 4 e to the minus Spalaron energy T over T. So this is my thermal transition rate when I have a non-zero Higgs expectation value. And the T to the 4th, okay, so this is the rate per unit volume. So the T to the 4th is essentially what you're getting on dimensional grounds. And this e to the minus energy over T is just a usual Boltzmann factor. It's a price you pay to have a thermal fluctuation at a given temperature over a barrier of a certain size. Very roughly. So this is my Spalaron rate when I have a non-zero Higgs expectation value. But I told you earlier that if you make the early universe hot enough, the Higgs expectation value actually goes to 0. And in this case, you actually lose the exponential suppression. It ends up being, okay, the full story is complicated because there are infrared divergences, but at the very least, at the very least, the exponential suppression goes away for these Spalaron transitions when you have a 0 Higgs expectation value. And okay, I'm going to write below the red line. My apologies, but I'm not going to go too far below the line. And it turns out that when I have a 0 Higgs expectation value in the early universe, and this happens at temperatures above about 100 GeV or so. We'll come back to this later on. My Spalaron rate goes like, per unit volume goes like T to the 4th with some number of powers of the weak alpha. So the weak alpha is just the G squared over 4 pi for the SU2 interaction. So this can be pretty small because I have an exponential suppression, at least at low enough temperatures. But this thing is really big. So on dimensional grounds, at high temperatures, this is about as big as you can get up to the alpha to the 4th factor. So the upshot of this is that if I heat up my universe enough, my Spalaron transition rate per unit volume becomes fast. It becomes fast relative to the rate of the expansion of the universe, and baryon lepton number violation in the early universe are just going wild. So if I heat above the phase transition temperature, roughly about 100 GeV, and my Higgs expectation value turns off, I get this really big transition rate, and I have full strength baryon and lepton number violation going on in the early universe. So this is going to be useful for baryogenesis. This gives us a big source of baryon number violation in the early universe that fortunately turns off today because of the big, well, temperature goes to 0, so I don't have these thermal fluctuations anymore. I'm stuck with instanton tunneling transitions, and the rate for those is tiny. So this is kind of the best of both worlds for baryogenesis. I have this great source of standard model baryon number violation at high temperatures, but it very conveniently turns off today, so we don't decay away. Okay. So this is the story for these SU2 instantons. It turns out that there also exist SU3 instantons, and you have a similar gauge theory vacuum structure. But the thing with SU3 instantons is that they don't change baryon or lepton number violation. But there's a similar story for them. And they can also play an important role for baryogenesis, but in a different way. So I want to move on. I spent more time on this than I intended to, but okay, it's an important topic. It's worth covering. Okay, so you probably have lots of questions about this. So I'm not going to ask if you have more questions. I'll be around at coffee and after in the next few days. But let me next turn on to CP violation, or C and CP violation. And this is the next ingredient for baryogenesis that we need. So this next ingredient for baryogenesis, C and CP violation, is probably going to be more familiar. So C violation is pretty straightforward. Suppose I just start off with a very simple theory with a complex scalar. So I just have some complex scalar field. Just something we're all familiar with. So as long as, well, given this Lagrangian, or even a fancier Lagrangian with a potential that only depends on the modulus of phi, the theory has a built-in U1 symmetry. And the another current corresponding to that built-in symmetry just turns out to be I phi star d mu left right phi, where this d mu left right is d mu acting this way minus d mu acting this way. So I have a built-in U1 symmetry. And now let's take this theory. At this point, it's just a free theory, and let's write down a mode expansion for it. So the mode expansion for phi, again, I just have a nice free field theory, is going to be, okay, in the normalization I like to use, 2 pi cubed, 2ek, ak, e to the minus I k dot x, plus bk dagger, e to the I k x. So it's a complex scalar, so there are 2 degrees of freedom. So I have independent so-called A and B mode operators. And the interpretation is, okay, so I'll come back to this in a second. So this is my mode expansion. If I write down my current, my charge corresponding to this conserved current, d3x j0, for the current corresponding to phi goes to e to the minus I alpha phi. If I write down the mode expansion for this current, it turns out that it just turns out to be dk tilde, ak dagger, ak, minus bk dagger, bk. Where this dk tilde is just my shorthand for this d3k over 2 pi cubed 2e cubed, just a Lorentz invariant integration measure. So the interpretation is that a dagger k creates things with positive charge, and we call these positive charge things particles. The b dagger k is going to create a particle with the same dispersion relation, so specifically the same mass, and otherwise all the same properties. And we call this the antiparticle. And this interpretation matches up with what we have from the current, sorry, from the conserved charge. This is just a number operator for the particle, number operator for the antiparticle, and my total charge is just ultimately the number of particles minus the number of antiparticles. Okay, so all this is just simple, straightforward free field theory. But within this context, we can very naturally introduce a charge conjugation operator. And the natural definition of charge conjugation is I just flip particles with antiparticles. So specifically under C, my A and B are just exchanged with each other. And this implies 2 things. First of all, under C, my phi of x is exchanged with my phi dagger of x. And my q, my conserved charge, goes to minus q. So this is the definition of a charge conjugation for this very simple complex scalar field theory. I have particles and antiparticles, and okay, this is just, okay, sorry, my apologies that my q's look like my phis. But this is the charge q, and that's my field phi, sorry. Okay, so this is charge conjugation this is charge conjugation on a complex scalar. We can get fancier and apply this to a Dirac fermion. So a Dirac fermion, instead of having this, a Dirac fermion would have a Lagrangian at the free level I gamma mu d mu psi minus m psi bar psi, with corresponding charge j mu if psi bar gamma mu psi, corresponding to the corresponding U1 invariance that you have built in here. And in the same way, I can repeat the story here, but I just have to put in spinors. But the slight tricky part when I put in spinors is that I also have these U's and V's. So instead of having this expression for my fermion, my fermion mode expansion psi of x is going to be a dk tilde times a sum over spin modes, u of k of s, ak of s, plus v bar k of s, b dagger of k of s, e to the I kx. So this is my mode expansion for fermions. The difference from the complex scalar piece is now I have to worry about fermion spin, so I've got these U's and V's, just the usual Dirac spinors. Now, my C operation, in the same way, is going to exchange the A's and B's. So again, you recall that the A dagger corresponds, the interpretation is the A dagger creates a particle of momentum k spin s, and the B dagger creates an antiparticle. So the action of charge conjugation will be to exchange A and B with the same spin state and same momentum. Now, when I go back and apply this to the field operator, I have to be a little bit fancier. And I have to be a little bit fancier because I also need to flip these U's and V's. And it turns out that the way to flip the U's and V's is to include some Dirac structure. So phi of x under C goes to minus I gamma 2 gamma 0 phi bar dagger transpose. And sometimes this thing is called psi sub C. And psi bar C goes to, how shall I write this? Psi transpose minus I gamma 2 gamma 0. So in the same way that I implemented charge conjugation on the complex scalar, I can do this for a Dirac fermion simply by flipping the A's and B's. But now because I also need to play some funny business with the U's and V's to make sense of all this, I have a slightly more complicated transformation law. So just in the 1 minute that I have left, in the 1 minute I have left, let me extend this to a vector boson. So for a vector boson, let's say something like a photon, we don't have an antiparticle, but we still transform the vector field for the following reason. So for example, suppose I look at QED. QED contains Dirac fermions, and the Dirac fermion part is invariant under C. But I also have a coupling E J mu A mu. Now, if you take this transformation law, you can show that it takes J mu into minus J mu, where J mu is the conserved current corresponding to the built-in U1 of the theory. So under C, this thing is invariant, but this thing goes to minus J mu. So as long as we also force our vector field to flip sign under C, we preserve the C invariance of the full couple theory. So this applies to QED. You can also do this for QED. You have to be a little bit careful because of the structure of the current now has SU3 matrices, but you can generalize this to QED as well. So the upshot is that regular QED and QCD respect this charge conjugation invariance, provided we define provided we also change the sign of the vector fields under the transformation. So I'm out of time, but I'm going to come back, well, I guess tomorrow, and talk about how this doesn't apply to the weak force, simply because I have chiral fermions. Okay, so again, thank you, and if you have questions, I'll be around for a bit.